Yeah, so we finished this topic. Here, a small summary for the elimination method. Yeah. All right. Goal, here you can see why the elimination method is so effective in problem solving. It is very effective. Yeah. The main reason is it can help us reduce the problem sizes. Reduce the size of problem. After the elimination, the size of the problem becomes smaller. So that's a good property we can take advantage of. Because this property, we use one statement here. So the smaller the problem size, the easier the problem. Here, the smaller the problem size, the easier the problem. Look at this sentence. Okay, this sentence. This sentence here, I want to explain the right way to understand this sentence. This sentence we treat it as a principle. Principle. Principle, all right? What's that? Principle. All right. All right. So because here, let me explain this principle later. When some elements do not change the outcome, they can be eliminated from consideration. So that's the basic idea. But here, let me explain this principle. Principle means most of the time it is correct, but it may not be always correct. Let's say in a simple way, when we talk about some principle, we mean 90% of the time it is correct. So we use it as a principle. So that means we try to follow this principle. Okay, we try to go along this direction, but we need to be aware of the situation that sometimes in some special cases, this principle may not be correct. That could happen. Exception, let's say, some exceptions could happen. Exceptional cases could occur not following this principle. That could happen. So there are exceptions. All right. Here I want to give you a simple example. Simple example to show you when the problem size is smaller, the problem could be harder than the difficulty of a larger problem size. That could happen. That's the exception. Okay? All right. So the problem is this. We learned that problem in our module 1. That's the prime factorization problem. Prime factorization problem. All right? In the prime factorization, given an integer m, what is the size? Because you only need to apply prime factorization on one given positive integer, only one number. So that is the size. The size in this situation, we mean the magnitude. Magnitude. Okay. It's not a number of elements in the array. Although most of the time we mean the size, number of elements in the array, but sometimes we only need to work on one given number. In that case, the magnitude of that number becomes the size of the problem. Now, so based on this understanding, let's look at the size number for prime factorization. When n1, the first n number, n1 equals 573, yeah. n2 equals 1000. Okay, so we have two different size numbers, and we need to do prime factorization. Now, which one is harder? Which one is simpler? Yeah. You can see the second one, when the size is larger, yeah, because the magnitude 1000 is larger than 573, and when we do prime factorization, it's easier, right? Easier, okay? Yeah. This one, although the size number is smaller, but when we do prime factorization, harder, right? Yeah. Because harder means we need to do more work, okay? Harder, yeah. You see? Yeah. So that's why this sentence, we use it as a principle. Yeah. So in the general situation, most of the time it is correct. So we try to follow this principle, but there are exceptional cases. Yeah. So we need to, we need to be aware of the exceptional cases that could happen. Yeah. All right. Yeah. So then we move to the next topic. Yeah. Impact of organized data, 8.2. Yeah. Yeah. In this topic, we want to solve a computing problem in two different ways. Yeah. One way, we use organized data. The other way, we do not use organized data. We just work on our data directly. Yeah. We want to compare which way is better. Yeah. All right, let's look at the question. Problem number 7. It's called element uniqueness problem. We want to check if in a given array, all the elements are unique or not. Yeah. Look at the question description. Given an array. Yeah. And how to check if all the elements are distinct. Yeah. So you need to find an algorithm. So then you write a function based on this algorithm. Yeah. If all the elements are unique, are distinct, then your function returns 1. Otherwise, returns 0. Yeah. Something like this. Yeah. Yeah. So it's a simple computing problem, but we have many different ways to solve this one. And we want to find the best way. Yeah. So we want to compare. Yeah. Which way is the fastest? Yeah. All right. Method 1. Yeah. Method 1, the brute force method. Yeah. So the brute force method, we just work on our data directly. Okay? Yeah. All right. Do nothing to organize data. Yeah. So we do not spend time, comparisons to organize the given data. We just do the checking directly. That's the brute force method. Okay, all right. In that case, good thing is we do not need to pay any cost on data organizing step. Yeah. Because when you organize data, you have some cost, right? You need to pay. Yeah, pay your computing resource. Yeah, so you need to use computing resource to organize the data. So there is some cost. Yeah. The brute force method, so we don't want to pay for that part. Yeah. We want to save. Okay. We do not want to do anything to organize the data. Yeah. All right. Now, so let's look at the comparison part. Yeah. So we have n elements. Yeah. So here, how to check if there is any element in this array that has duplicates in this array, duplicate values in this array. Okay, yeah. So when you do the checking, yeah, so you need to check, you need to do comparisons based on each element, right? Yeah. For example, for the first element, is the first element unique or not in this array? Okay, you answer the question. First element. After that, you may need to answer the second. Is the second element unique or not in this array, and so on. For each element, you need to answer this question. Right? Yeah. That's the brute force method. Okay? Yeah. All right. Yeah. For the first element, when you do the checking, you need to compare the first element with all the remaining elements. Right? Yeah. For the worst case, at least. Yeah. For the best case, when you compare the first element with the second element, then they happen to be equal, then your function terminates. Okay? Yeah. You can read your function returns 0, let's say. Yeah, 0 means not unique. Okay? Not unique. Yeah? So the best case is one comparison. Yeah. But the worst case, yeah, you need to compare the first element with all the remaining elements. The n minus 1 comparison, the worst case. Yeah. All right. Yeah. Here, let's calculate the worst case. Yeah. After that, yeah, we need to check the second element, if the second element is unique or not. Yeah. For the worst case, n minus 2, and so on. Okay? Yeah. All right. Yeah. The second to last, one comparison. The last one, we do not need to do any comparison. Yeah. Only one element left. Yeah. All right. So now we can count the total number of comparisons for the worst case. Yeah. Now, we're interested in the worst case here. Yeah. All right. Yeah, because best case is very simple. Yeah. So, just one. Yeah. The worst case, yeah. So we need to, yeah. Here, this is the example. The numbers here, yeah. So that's the, the concrete numbers. Yeah. We use these concrete numbers as our data input. Yeah. So here, one special case, when only the last two elements are the same, the function returns 0, right? Yeah, not unique. Yeah, yeah. But that's the worst case. Yeah. Although, if all the elements are unique, also the worst case, right? Because if the elements are unique, you need to go through all the possible comparisons for checking, right? Yeah. You cannot miss any possible case. Yeah. Yeah. So the worst case, we can calculate the total number of comparisons. So this number. Okay? Yeah. All right. That's the method 1, brute force method, worst case. Yeah. All right. Average case efficiency, yeah. So average case efficiency, so then you need to, do a little more work. Yeah. For each element, yeah, you look at the average case, the number of comparisons. Yeah, pretty easy. Yeah. So then you add up, yeah, average case numbers, for all the cases. Yeah. All right. Yeah. But here I do not spend time on it. Yeah. But the second, this time we are willing to pay to organize data. Yeah. So this time we want to see if we spend some of our computing resource to organize the data, can we do better? Yeah, that's an interesting question. Yeah. Yeah. So our method number 2, yeah, we want to do preparation. Yeah. The first step, we prepare our data. How to prepare the data? We organize the data. Okay? Yeah. So we treat the spending for that part, it's investment. Yeah. Because we will get some gain. Yeah. Yeah. Later, we can take advantage of the nice properties from the organized data. Yeah. All right, so let's see. Yeah. How to organize data? Yeah, very simple. We sort the array. Yeah. Sorting is a simple way to organize data. Because after sorting, the unordered data becomes ordered data. The structure, the ordered data, this structure is very useful in our main step of data processing. The main step is checking for uniqueness. Yeah. That checking step, we can enjoy the nice properties of organized data. Yeah. So that's why we call it, yeah, the amount we pay in that step, we call it investment. Yeah. Because we will get a lot of gain next. Yeah. All right. Yeah. Yeah. Sorting the data. So here I want to use the best sorting algorithm we can get. The selection sort, we have learned that selection sort, but that efficiency is not good. Yeah, very poor. Yeah. Yeah. Very poor. Yeah. Later, we will learn many other sorts. Yeah. The best we can get is n log n. Yeah. For the worst case, yeah, so this n log n, remember, we're targeting the worst case. We're targeting the worst case. Yeah. The best sort, yeah, or the sort with the fastest worst case efficiency, yeah, that is this n log n. Okay? Yeah. So there are several sorts that can give us this worst case efficiency n log n. Yeah, here, let's just use it first. Yeah. Later we will learn the details of those sorts. Yeah. All right. That's the preparation step. Yeah. That's the cost we pay in the preparation step. Yeah. This much cost. Yeah. All right. Next question, how to check if element is repeated in an order? Yeah, because after that, we only need to work on the ordered data. So that's much easier than unordered data. Yeah. How much is the difference? Yeah. So let's do some analysis to see the difference between ordered data and unordered data for this question. Yeah. All right. For ordered data, yeah, ascending order. Yeah, let us assume, yeah, we have the data ascending order. Yeah. Then think about, yeah, if some of the elements have duplicates in this array, they are repeated in this array, what would happen in this ascending ordered data? Data with ascending order. Yeah. Yeah. Try to, use your intuition to think about the form of your data. Yeah. Suppose one element is repeated a few times in this array. But after you sort this array, yeah, all the elements with the same value should take the consecutive locations, right? In an ordered data, in an ordered array. Yeah. Those elements with the same value should occupy consecutive locations. Yeah. So that's the simple fact. That's the simple fact. So this property, we can take advantage of this property to improve our checking, efficiency of our checking step. Yeah. All right. That's the observation. We only need to compare two adjacent elements. Yeah. So based on that observation, all those elements with the same values must occupy consecutive locations. Based on that observation, we can make our decision. So this is our decision. So the observation is, let me write here, all the elements with the same value must occupy consecutive locations. Yeah, that's the observation. Okay, yeah. Based on this observation, then this is our decision. Yeah, because we make our decision based on this observation. Yeah. When we do the checking, we only need to compare two adjacent elements. Yeah, because consecutive locations, adjacent comparisons is good enough to help us find repeated elements, right? Yeah. Adjacent comparison is good enough. Yeah. So that's the reason the organized data, the ordered data, can help us save a lot of comparisons. Yeah. All right. So now, yeah, the pseudocode to do, because only an adjacent comparison. Compare between A of I and A of I plus 1. Two adjacent elements. Yeah. If they are the same, so you'll find one repeated element, the function returns false, true or false. Yeah, false. Means not distinct. Yeah. Yeah. Very simple. Yeah. Then, if we do analysis for this step, you can see, how many adjacent comparisons do you have? N minus 1. See? Yeah. So you can see this fact easily. Yeah. Let me use simple diagram. Suppose we have position 1, position 2, position 3, the last element position n. Yeah. First adjacent comparison between first two elements. Second adjacent comparison, and so on. Okay? The last adjacent comparison. So then the total number of adjacent comparison, you have total n minus 1 adjacent comparisons. Okay? Yeah. And for worst case, yeah, you can see, for the worst case, this is the worst case number. So this step, you only need to do n minus 1 adjacent comparisons. That's the improvement. Yeah. Yeah. But yeah, you still, when you calculate the final total number of comparisons, you need to include the preparation. Yeah, because that's the cost you pay for the preparation step. You should include it in the final round counting. Yeah. Yeah. So these two numbers adding together, that's your final number of comparisons. Yeah. All right. Yeah. So there. Yeah. All right. So next topic, part B, growth function. Still, in this part B, we will continue the discussion of that uniqueness. Yeah, because we haven't do the comparison, right? Yeah. But we move to the topic of part B. Yeah. But before that, yeah, let me do some summary. Yeah. Because right now we have these two methods. Let me do some summary, yeah, before we move to the part B. Yeah. Yeah. For these two methods, method 1, method 2. Okay? Yeah. Method 1, so we use unordered data. Unordered data, the difference. Method 2, we use ordered data. Okay? Yeah. Difference. Yeah. Yeah. For unordered data, when you do the uniqueness checking, that step, uniqueness checking, yeah, you need to do, what do you need? You need to do global comparisons. Yeah. So that's the, typical work you need to do. Global comparisons. Yeah. You need to compare all the possible pairs. Yeah. All those global pairs. Now, the two elements for your current comparison come from the array globally, anywhere in the array, any positions in the array. Yeah. So that's what do we mean? A global pair. Yeah. All right. And ordered data, you only need to do local comparison. Yeah. Actually, yeah, even better than the local. So you only need to do adjacent comparisons. That's the key difference between these two methods. Yeah. Global comparisons versus adjacent comparisons. Okay? Yeah. So that's the, main difference between these two methods. But in order to make the adjacent comparison work, yeah, So you need a preparation step. Preparation step. Yeah. The first method, you do not need a preparation step. Yeah. Because nothing is free. Yeah. To get all the data, it's not free. You need to pay quite a lot. Your computing resource to get organized data. Yeah. So it's not free. Yeah. Yeah. All right. Yeah. So that's the summary. Yeah. All right. Now let's move to part B, growth functions. Yeah. So we will, prepare ourselves toward this topic, analysis of algorithm efficiencies. Yeah. So this topic is very abstract topic. In order to understand, yeah. So actually, we will in this module, the main concept we will learn asymptotic notation. Asymptotic notations. That's the main topic of this module. Yeah. Yeah. And very abstract. This concept very abstract. So we need to do a lot of preparations to understand this concept. Yeah. All right. Yeah. So to start a discussion of this concept, yeah. So let me just make the connection, yeah, because our topic in the previous part A, yeah, will be continued in this part B. Yeah. So we make some connection, yeah, here. All right. Here, so let's compare, yeah, difference from the previous part. Yeah. The first method, we need to do global comparisons. Okay? The second method, we need to do adjacent comparisons. All right. Why this is a big improvement? From global to adjacent. Why is a big improvement? We want to see it, right? Why this conversion, this transformation, this kind of data transformation is a big improvement. Yeah. So let's do the counting. Let's count number of global pairs, right? Yeah. Because when you do global comparison, you need to work on the global pairs, right? Yeah. How many global pairs do you have? From an n element array, yeah, this many. Yeah. We count many times, right? Yeah. 1/2 times n minus 1. Yeah. That's the number of total global pairs. Yeah. All right, so let's count the number of adjacent pairs. From the previous slide, we have that number, n minus 1. Now you can see how much is the difference. The reduction from 1/2 times n minus is reduced to n minus 1. That's a big improvement, right? Yeah. So the investment you pay in the preparation step, sorting, the gain, this is the gain you get. The gain from the investment you pay in the preparation step. Difference is this much. Okay? Yeah. The gain. Yeah. All right. So that's the connection. Yeah. So now let's move to the second topic. Yeah. Formula between running time and the number of basic operations. Yeah. Here, let me first talk about some concepts, growth function concepts for the preparation of our asymptotic notations. Yeah, do that part. So after we learn asymptotic notations, then we will apply, yeah, because we haven't complete the comparison part, right? Yeah. In the part A, we have method 1, we have method 2, but we don't know which one is faster, right? Yeah. We do not know. Is method 1 better, faster, or method 2 better, faster, right? Yeah, because method 2 has the preparation step. Yeah. That preparation step probably, yeah, slow down the overall performance. There is a possibility, right? Yeah. The computing resource, the time we spend in the preparation step, probably not worth, right? Not worth the amount we pay, right? Yeah. So we need to investigate. We really need to do some serious comparison on that part. Yeah. But we delay a little bit. Yeah. So we will get there. Yeah. Yeah. Because before we do that comparison, we want to learn the asymptotic notations first. Yeah. Because when we do comparisons, we will apply the knowledge on the asymptotic notations to understand the difference. Yeah, so that's the reason. Yeah, so we delay a little bit. Yeah. All right, so let's do the preparation, yeah, for the asymptotic notations. Yeah. We need to understand the goal. So why we study asymptotic notations? Yeah. All right. Yeah. First, let's look at the general notations. Yeah. Functions of running time function. Yeah, we use capital T. Yeah. The variable n. Yeah. The data size. Yeah. So this n is the data size. Capital T of n represents the running time function for a particular algorithm. Yeah. Yeah. All right. The first notation. Another second notation, we also need to use a function of number of basic operations used. Yeah. Basic operation, what's the basic operation? Yeah. So I mentioned in the last lecture, yeah, but actually I didn't elaborate. Yeah. Yeah. The basic operation. The most commonly used operations in one algorithm, we call it basic operation. The operation that you spend most of your time in this operation, the basic operation, the dominant operations. Yeah. All right. Operations contributing the most to your total running time. Yeah. That's we call the basic operation. Yeah. All right. Then we also need another notation, execution time of one basic operation, little c op. Yeah. Yeah. Because that constant number, so this is a constant number, yeah. It is useful to make connection between these two functions. These two functions, they are co-related. How to connect these two functions? We need this constant, COP. Yeah. So each basic operation, yeah, the average execution time, yeah, because here the best way to for that is the average execution time, because in the real world execution of your computation, yeah, for each same of the operation, every time your CPU execution time could be different, right? Yeah. Yeah. Because your CPU, yeah, the running environment could change. Yeah. 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 Remember, so in your computer CPU, usually the CPU will be used for multiple tasks, right? Yeah, multiple tasks. So CPU needs to work on many different things. Yeah, yeah. So for that reason, every time when your algorithm is executed, yeah, the specific real time could be different. Yeah. So that's the, you know, yeah. But here, we do not need, you know, exact execution time. Yeah, approximately. Yeah, approximately execution time. Yeah. Yeah. All right. So that's you know, a small problem. Yeah. Formulas. Yeah, we want to connect these two formulas. Yeah. So we take approximation approach. Yeah. It's very hard to get exact expression. Yeah. So we can accept approximation approach. That is, capital T of n approximately equal to constant little c up times capital C of n. Yeah. 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 So this formula connects these two functions, capital T function, capital C function. Yeah. Yeah. These two functions are proportional. Yeah. The constant used in the proportion is this little c up. Yeah. All right. So then, yeah. So why it is important? Yeah. Yeah. Because remember, yeah. The capital T function, that's the running time, that execution time. Remember, last time when I talk about measure of efficiency, right? So when I talk about measure of efficiency of computer algorithm efficiency. Okay, yeah. You can use the running time function to measure, but it's unstable, right? Yeah. Unstable. Yeah. And you can use this counting number as the measure. That is a stable function, a stable measure. Yeah. So here you can see when you connect unstable measure and a stable measure, yeah, the connection is so simple. Yeah. Proportional. Yeah. Yeah. So that's the importance of this formula. Yeah. So you can convert, actually you can convert unstable measure to stable measure by this simple formula. How about that? Yeah. Then, yeah, but you have a special constant involved in this formula. Yeah. Next, we want to look at the role of this little constant. What's the role it plays here? Yeah. All right. Yeah. Yeah. So ignore unnecessary detail. Yeah. So here, approach. Yeah. So now, look at the goal. Yeah. Our goal here. Yeah. Goal. So what we are doing here, right? We need to know our goal. Yeah. What are we doing here? Yeah. Our goal, yeah, described efficiencies of computer algorithms. That's our goal in this module. Okay? Yeah. Otherwise, we get lost, right? What we are doing here? Yeah. So we want to find a good way to describe the efficiencies of computer algorithms. Yeah. Efficiency. So you cannot use the capital T function because it's unstable, right? Yeah. So we should use this capital C function. It's a stable measure. Yeah. All right. Then, so now we are at this point. C function is a good measure, right? Good measure for efficiencies. All right. Yeah. But we cannot stop right here. Yeah. Because although it is a good measure, yeah, but when we discuss the efficiency functions for all the computer algorithms, yeah, so here, this is our efficiency algorithms. So we use this capital C functions to describe efficiencies of algorithms directly, yeah, but we have more work to do. So we're not satisfied at this point because there is another important step we need to do. We need to compare the efficiency of different algorithms. Yeah. So that's another important step. Yeah. So we need to compare, okay? Yeah. Compare efficiencies of algorithm. Yeah. We need to compare the efficiencies functions. Which one faster, which one smaller? All right? Yeah. So here's the question. Yeah. What is the best way to do the comparisons? Yeah. Because the efficiency functions could be very complicated. So how do you compare complicated efficiency functions? So that's the main question. Yeah, we need to answer in this part. All right, yeah. Yeah. So we want to simplify our expressions, right? Yeah, we want to simplify. Yeah. Remember, in our linear search, we ignore minor terms. We keep the dominant term. That's the way we simplify efficiency function. Yeah. So one question we want to see to simplify efficiency function, ignore some constant. Yeah. Ignore some constant. All right? Yeah. So let's think about that. Can we ignore some minor terms? Yeah. So some constants, some minor terms. Yeah. So, but when we do that, we need to, put these things under control, right? Yeah. Under control. Because when you simplify it too much, yeah, you don't want to make it out of control. Okay? Yeah. So you want to maintain the control when you do the transformations. Yeah. So this time we do transformations on our efficiency functions. We will change the forms of efficiency functions. To make it simpler, we will make our efficiency functions much simpler without losing the main portion of the efficiency function. We still want to maintain the main portion of the efficiency functions. Yeah, all right. Yeah, yeah. So here, to see that, so this time we want to see the rho of the constant. Yeah, let's take a ratio of these functions. T of 2n over T of n. Yeah, T of 2n. So that means when you double the data size, now you want to see the ratio of your T function. Yeah. After you double the size and before you double the size, you take the ratio of the running time function. Yeah. Yeah. So by this formula, you can see the ratio for the T function when you double the problem size approximately the same as the ratio of your C function when you double the problem size. Yeah. And when you consider the ratio, yeah, so when you consider ratio there, this little c constant is gone. This constant is gone. Okay? Yeah. Yeah. And yeah, so when you look at the ratio of this, you don't need to look at that little constant. That constant. You can ignore. In other words, you can ignore that constant. Okay? Yeah. And this ratio can give you some increasing rate, right? Increasing rate of the function, right? Yeah. This ratio, yeah, you know, the function value is increasing. Yeah. The larger the size, the larger the function values. In general, here in general, yeah. There are exceptional cases. We know there are exceptional cases. Yeah. All right. So this ratio in general, yeah. So it's increasing. Yeah. But how large is the increasing rate? Yeah. Here, oh, yeah, I reached the end. Yeah. So let me just finish this slide. So that next time we continue this topic. Yeah. All right. So this ratio gives us kind of increasing rate. Yeah. Yeah. Kind of. Yeah. So yeah, because roughly, it's a rough way. Yeah. Rough way. Yeah. All right. Yeah. Yeah. So give us some information related to the increasing rate. Yeah. All right. Yeah. All right. Let me stop right here. Yeah. So next time, so we will do more discussion on this topic. Yeah. Oh, one thing before you leave. One last thing. In this weekend, I plan to post our quiz number 2. Okay, quiz number 2. So then next week, after the first lecture next week, I will give you our first homework assignment. Yeah, just let you know. Yeah, our plan. Yeah. All right, that's it.